Hi everyone. Hey, let's get started with Physical Science 5, looking at Chapter 1. And we're not going to cover all of Chapter 1, we're just going to get us started. So this is just Part 1. If you haven't had a chance to look through the textbook, you should, but here's some highlights. Some key concepts are mass and weight, and you should be familiar with their differences. Let's see, mass, one definition might be a measure of the amount of matter. And weight, that might be defined as the force of an object due to gravity. Now here on the surface of planet Earth, we oftentimes use these words interchangeably. Something is a really massive object or something weighs a lot. They both kind of convey the same idea. However, if you go into outer space, there's a little astronaut here, we say that in space you are weightless. Which is a good statement. You don't weigh anything. Your weight is zero. Yeah, this astronaut isn't falling to Earth. It's just kind of floating there. He weighs nothing. But if you try and push on him, you're going to feel some resistance. He still has mass. So you still have mass. So it's kind of a measure of how much material, how much matter, how much bulk, weight, makes up the astronaut. Mass, well, when we're measuring mass, the common unit is pounds, but in science we like to use the metric system. So the unit's going to be kilogram, abbreviated kg. Force, on the other hand, well, there's lots of units for force. We're going to use newtons. Newton, capital N there. Let's see, a 1 kilogram rock. Okay, that explains how massive it is. It's a kilogram's worth of material. Well, we're going to say that weighs about 10 newtons. Okay, now in Physical Science 5, we're just looking at a broad stroke, this kind of a surface understanding of science, beginning with physics. So that's good enough for us for this class. Some of you may want more information, like, hey, I thought we weigh stuff in kilograms. And again, that just has to do with the planet Earth. If you want a little bit more insight into that, here's a little bit extra. This is extra. Put that in parentheses. Extra, meaning we'll deal with this later, not right now in Chapter 1. But weight can be defined as equal to the mass times acceleration. Sorry, 2c there. Acceleration due to gravity. And again, we'll talk about gravity a little bit later. But there we go. And in algebraic terms, we might say, or some room here, W equals mass times g, where g is a value, a measurement of the acceleration of gravity. Okay. Again, that's extra. We'll get into this later. For now, be familiar with newtons. We see a number followed by the letter N. That's talking about a force, a weight force. And if you see units of kg, we're talking about mass. Inertia, another term we need to be familiar with. Inertia is the property of an object to resist changes in motion. you can also think of mass as a measure of inertia. So right down here, I did a little surfing on the web and found this Hummer made of styrofoam. Sorry. There's a real Hummer, and I bet this guy here could probably lift up the corner of this Hummer. Styrofoam does have some weight. It definitely has mass, but it's not nearly as massive as the real Hummer over here, which has a great more deal of weight, right? Okay, so mass and weight there. This is less massive. This one's more massive. But if they're both in motion, rolling down a hill, which one are you more concerned about? Which one do you want to get out of the way of a little more quickly? Yeah, the big Hummer here, it carries more mass, and it's going to resist changes in motion, meaning if you're in the way, you're not going to be able to slow it down very easily, because all this mass moving down the hill is going to keep on moving down the hill and just bump you right out of the way. Ouch. Whereas a styrofoam, looks like this thing could roll. Assuming it does roll down a hill, yeah, I don't know, that might be uncomfortable being hit by such a large object, but you'd probably be okay. In fact, this will probably stop or bounce off of you, because you just might have enough mass so your inertia resists changes of motion and forcing this styrofoam Hummer out of the way. Okay, and now we're talking about motion. Let's talk a little bit more about that. If we talk about speed, how fast an object is going, that's a single quantity. Single quantity. And oftentimes you might talk about velocity and speed in the same terms, but in science, velocity means something else. In addition to speed, it also means direction. So if you talk about velocity, you need to talk about which direction a vehicle is moving. Not just what the speedometer says, how fast it's going, but also what direction it's going. And there's several other quantities that has this dualistic behavior where you have size and direction, and for such things we call them vectors. Velocity is defined as a vector. Forces are defined as vectors. Gravity pulls down, that's a direction. Oh, if a car travels around a corner at 25 miles per hour, well, speed doesn't change. But its velocity does. And that's because it's changing its direction. It's rounding a corner. It might be going north as it approaches the intersection, and as it turns, let's say it turns to the right, well, then it's heading east. It's a different direction. And even if the speed is constant, well, velocity is not just speed, it's also direction. Let's see, we got the equilibrium rule over here. The book defines it one way as the velocity of an object. If the velocity of an object is not changing, then the vector sum, there's that word vector sum of forces equals 0. I refined it a little bit differently over here. It means the same thing, I think. If an object does not change its speed or direction, then all the forces on the object are canceling out. Okay. It's actually a really practical rule. In the next video, I'll give you an example where we can use it to understand the system a little bit better. Here's some supporting ideas we're going to use when we talk about equilibrium rule. The first one is support force. And this is, or you know what, this is sometimes called a normal force. for those who have seen some physics before. I don't know why the letter R isn't showing up. There we go. The normal force, it's the force that opposes gravity, or the force that is opposite gravity. And so instead of me drawing a little stick man, well, that's interesting. I found this little picture here. Got this person standing on a bathroom scale down here, and his weight force, he weighs something. He has mass, and gravity's pulling him downward to make that gravitational force. His weight, that's this arrow here, is pushing down and pulling him down towards the center of the earth. Well, he doesn't keep traveling into the earth and keep going. And that's because the scale here and the floor underneath it is resisting that downward force. It's actually pushing up. The force of the scale pushes the force up, and we call that the support force. And the equilibrium rule says if this guy isn't falling into the floor, then the support force and the gravitational force have to cancel. All the forces cancel out. And then what's kind of cool, at least from a scientific point of view, is if you know the weight force, let's say this guy weighs, I don't know, 400 newtons. That downward force is 400 newtons. Well then, if he's not moving, if he's at rest, the velocity's not changing, it's actually 0, then we actually can calculate the support force. Well, it has to be the opposite of the weight force. So support force is actually 400 newtons pointing out. Opposite directions, same size or magnitude, and they cancel. Let's see, last idea. It's also going to be useful when we talk about support, the equilibrium rule. And that's tension. That's the force in a rope or cable, or down here as a rubber band, when both ends are pulled in opposite directions. Okay, this relaxed rubber band over here has zero tension in it. There's no force. And over here, this finger's pushing the rubber band out in this direction. This finger's pulling the rubber band in this direction. I should make those arrows about the same length, because I'm assuming this is all at rest. Someone's just holding the rubber band in this position, getting ready to launch the rubber band in some direction. And the idea, the rubber band and the fingers are not moving. Okay, so the equilibrium rule says, hey, these objects, the rubber band, the fingers, those objects are not changing their velocity. So in fact, all the forces must be canceling out. So this finger here is being pulled back this way. Why doesn't it keep on going backwards? Well, the rubber band is creating a tension opposite that and pulling the finger forward in this direction so that the finger's at rest. What about this finger? Well, the equilibrium rule says if this finger isn't moving forward, or isn't changing its velocity, I should say. Let's say it's at rest, so the velocity is not changing, it's actually 0, and this hand is trying to push the finger out in this direction. Well, there's a tension in the rubber band that's pulling back opposite this with the same size to cancel out that forward force. All the forces are canceling out, so it's a rest. Okay, I think that's enough for chapter 1. Let's stop there. Take another look at the following video. We're going to have an application of the equilibrium rule. Thanks for watching.